Rajshekhar garu ready na?
Yes, sir. Sir, I request Anil sir to give a brief introduction about our today's speaker. Anil sir. Sir, unmute చేసుకోండి.
Yes, sir. Yes, sir. Yes. Good morning to one and all. Myself, P. Anil Kumar, Assistant Professor of EC Department, Gudlowalle Engineering College, Gudlowalle. It's my privilege to introduce the today's speaker, Engineer Surabhi Bhavani Shankar garu. He obtained his MS degree in electronics from Andhra University, Visakhapatnam in 2006. Currently, he is working as Executive Manager for the Electronic System Private Limited, Vijayawada. Engineer Bhavani Shankar garu heading IoT Services Department in Electronic System Private Limited. So he is instrumental in the growth of the organization and in positioning the company as one of the India's smart solutions company. With the support of his R&D activities, Electronics is now a leading provider of smart solutions for Indian railway signaling and smart cities and smart buildings. He played various responsible roles in the development of various R&D projects, and some of the R&D projects are remote condition monitoring system for Indian railways and IoT-based smart water distribution management system and intelligent transportation system solutions and smart appliances control and smart LED control. And some other responsibilities of the engineer Bhavani Shankar garu are he involved in the digital transformation initiatives of the company, and he is a member of the Board of Studies, JNTU Kakinada, EC Department, and he is a member of Board of Studies, BVC Engineering College, Odal Rail. And he is an industry expert for various engineering colleges, and he helped in the improvement of the syllabus and teaching learning process. So with this short introduction, I kindly request Engineer Bhavani Shankar garu to take over the today's session. Thank you, sir. Thank you, one and all.
Bhavani Shankar garu, please welcome to our third day session 1. Thank you, sir. Sir, if possible, at the beginning, you please in video mode at the beginning. Later on, you may switch it off your video mode. Bhavani Shankar garu.
Yeah, sure.
Yes, sir.
Uh, 1 minute, Kamaraj garu. I'm setting up my.
Sure, sir. Sure, sir. Got it, sir.
సార్ ఫుల్ స్క్రీన్ వస్తుందా లేకపోతే how it
ఫుల్గా వస్తుందండి, ఫుల్గా వస్తుంది. బిగినింగ్ వీడియోలో మాట్లాడండి సార్, లేటర్ ఆన్ యూ మే స్విచ్ ఆఫ్.
yeah. So it's fine. Okay. Good morning, everyone. This is Bhavani Shankar. I welcome all of you for the third day of the National Faculty Development Program conducted by GEC in association with ATAL from AICTE. So today, I hope all of you might have gone through the fundamentals of IoT, various other aspects of IoT solutions, either it is intelligence in IoT, whether it is ML or AI, or power supplies and other areas, sensors and all, communication technologies, protocols. Now in this session, I will exclusively deal with the reference architectural model of IoT and emphasize on the edge processing, why it is required and what constitutes edge, what are the fundamental activities that is performed in edge processing and all. And also I'll give you an overall big picture of a IoT solution, or total all components clubbed together. So this is the agenda for next 1 hour. So for 15-20 minutes, I'll allow you for raising questions and I'll answer it to my capabilities. So let me initiate the slideshow and I'll explain one by one. Okay. You all can see now?
Yes, sir.
Okay. So IoT, there are a lot of hype around that. No doubt, it is very true. Basically, when you talk about Industry 4 revolution, the basis for Industry 4 revolution is the digital foundation. And that digital foundation is essentially provided by the Internet of Things. Because if you don't have that Internet of Things as a baseline architecture, part of the Industry 4 total transformation, it is very impossible for the machines to communicate, systems to communicate, take decisions based on the data. So IoT fundamentally provides that digital foundation that we all should be knowing that, because going forward, you cannot straight away jump into artificial intelligence or other digital twins kind of higher end technologies before actually knowing in and out of IoT. IoT essentially, when we say intelligence, that means there is some form of ability to think, ability to decide and act, right? So if you apply the same analogy to the devices, ability to sense the physical world, like our human body has ears, eyes, and we feel, we smell, we see things. So there are various sensory organs in our body which enable us to understand the physical world. Similarly, if a physical device or a physical system also have the ability to sense the physical world, and like the sensory organs communicate the information to the brain, there should be some sort of connectivity wherein the entire sense or captured information is communicated to the central intelligence core, where it gets analyzed in terms of context, in terms of its internal states, and decisions are made and subsequently actions are initiated. So same like a human body performs, the ability to sense, think, and act, if the machines also do that, independent of human interventions, that's where we call it Internet of Things. So what is IoT? Many people might have told you different sort of definitions. But let me simplify for all of you what is IoT. IoT is a network of physical or virtual things which have the ability to capture information in real time through various means like sensors, things, and apps, which have the ability to communicate through wired or wireless communication technologies or interfaces or protocols, and analyze the information on the fly in real time and derive insights from the data, and finally act upon those insights through data-driven decisions and finally achieve the value outcome. So we are talking about network of physical or virtual things which have the ability to sense, communicate, analyze, and act. Then only we can call it as a IoT, not just simply having the ability to push the data into cloud is not IoT. IoT should have all these ingredients. If we look at the architectural model, here you can see we have defined 5 layers, 3 tiers, bottom, edge, platform, and enterprise tier. And we have interfaces if you closely observe. So this is a reference model. Many people have given different kind of architectures. Still standardization is not yet done. But in a nutshell, this is the reference architecture for the IoT, which unanimously across industry we accept and we are following. So let me define 3 building blocks of this reference model: layer, tier, and interface. Layers actually define what capabilities an IoT component, function, or process must have. So layers define the capabilities. We have 5 key layers here: device layer, which is nothing but physical layer, communication layer, information layer, function layer, and process layer. Whereas tier, if you see 3 tiers are there: edge tier, platform tier, and enterprise tier. Tiers define where to deploy that particular component, function, or process. So layer defines what capabilities that component, function should have. Tier defines where exactly it need to be implemented or deployed. We have 3 deployment areas. One is at edge, which I will elaborate much more in detail in later stages. Second is platform. Third is the enterprise level. Whereas the third building block we are talking is interfaces. Interfaces define how the data and control flow into and out of the entire system. So there are 2 types of interfaces. One is cross tier, that means across tier on the x-axis, and communication across y-axis, that is across layers. So cross tier, cross layer. We have 2 types of interfaces. If we look at this entire reference architecture, we need to answer these 3 questions. One, what functionality is required. That means there are various IoT use cases, whether you are building a predictive maintenance for a asset or machine, whether you are building a some kind of intelligent air conditioning control, or you are building some sort of immersive experience for user. So it could be whatever, any functionality. So the first question should be what functionality is required. The second is where that functionality will operate. For example, in the entire problem space, we have divided into various functional modules. Which functionality should run on which tier? That means whether we have to run at the source of data itself, whether we have to run in a centralized location within a building or a premises or a facility, or we have to deploy and run in the cloud. So where the functionality will operate. The third, how data and control will flow through the system. There are various data and control flow models, whether it is event-driven model or service type of thing, or it is a streaming kind of a thing. Whatever it is, so we need to answer these three fundamental questions. So let us first examine the types. So like I said, there are three types in the IoT architecture. One, the edge type. What does edge mean? Edge mean close to the source. That means wherever data is getting generated, there only we have to do some finite elementary analysis and processing, which we call it as edge. So if you look at edge here, interestingly, edge is where the data is getting sampled, because all your sensors, actuators, everything is near to that. So edge tier is where data is captured, collected using variety of physical devices like sensors, intelligent things. These things can be a simple commercial gadget like a thermostat, or an appliance like a AC, or a system like a centralized air conditioning monitoring system, or a physical controller like a actuator which will on and off the air conditioning system. So that entire physical layer consists of these sensors, devices, and controllers. So the edge tier essentially perform the basic sense and also perform some localized data processing. You can see in the diagram in the edge tier, there is a specific component called IoT gateway. What does gateway do? Generally, gateway is more like a provide access to various kinds of interfaces and provides the ability to aggregate information. That means in a physical world, we will have various sensor networks, various device networks, So there should be some localized aggregation that is possible through IoT gateway. And this gateway or edge device is capable of performing localized data analysis, event processing, and also store certain information internally. Because whenever there is a communication break to the higher application layers, the gateway or the edge device should be capable enough to store the data so that there is no data loss. And also these edge devices play an interesting role your existing infrastructure might be quite old. Different kind of interfaces the device might have, the legacy systems, legacy protocols, legacy electrical interfaces and all. This gateway will act as a bridge to those legacy devices and higher order IoT platforms by converting that data into relevant protocol understandable by the modern IoT platforms. So essentially, what are the activities gateway is doing right now? Edge device, perform localized analysis, process the data, that means refine it, store internally, and translate that information from one form to another form, like protocol conversion, and exchange the information through the long-range communication with the platform layer. So this could be either through WebSocket or MQTT or COAP. There are various kinds of IoT protocols, which I suppose yesterday you are exposed to those things by another speaker. So this is the edge tier. Now look at the second component, platform tier. This is where the IoT system as a whole aggregates system-wide data. And that means we are getting various Kamaraj, can you see the slideshow? Full screen convert na? Three types of IoT architecture.
Confusion, sir.
Okay.
Yes, sir. Edge tier, platform tier, and enterprise tier.
Okay, right.
Yes,
thank you. The platform tier is where the IoT system aggregates the system-wide data and events from many locations. That means edge tier, you can consider it as a location where localized data capturing everything happens, and through gateway it is sent to the platform layer. So essentially what platform layer means, it is aggregating various data commands, data events coming from various edge locations, looking at a system level holistically. Now what does it do? If you look into the internal of the platform tier, one, it will do device management. That means it acts as a authentication, configuring the devices and managing the devices in the entire IoT network. So the first part is the device management it performs through edge device authentication and gateway services. The second, that in the context of processing, we are getting events and commands. So there are two processing capabilities. One, processing the streams, real-time data streams, process the complex events which are coming out of this edge network. And the third capability is to perform analytics. It can be simple business intelligence or a simple descriptive analytics, or more complex machine learning and advanced analytics. And additionally, the fourth capability of platform tier is it also performs orchestration. That means it will invoke the enterprise applications when and where it required. So that is the platform tier for you. Generally, these platforms are provided by various IoT platform vendors. It could be Microsoft Azure platform, AWS platform, or it could be Google, or it could be Hitachi, it could be ThingWorks from PTC, and there are various things. Or IBM, Siemens, we have various platforms for various kinds of use cases. No single platform is capable enough to address all the requirements of the system. So essentially what you're going to see is this IoT platform is more like a loosely coupled thing. It is not robust. It is a loosely coupled. Still, they are still evolving. As of now, they are loosely coupled. You should understand that. And it could be single platform or amalgamation of various platforms together. So your platform tier is that. The third tier is the enterprise tier. Enterprise tier is where IoT integrates with set of business application processors and higher order services required to run a particular business objective or achieve a particular business objective. Because at an enterprise level, we are looking at a total business as a whole. For example, edge tier, I'll give two scenarios here. One real world scenario like a smart city. Smart city, if you look at, edge means there are various sensors, devices and subsystems deployed across the city. Which could be traffic management system, which could be surveillance system, which could be citizen governance related system, which could be public addressing system or guidance system, which could be environment monitoring and air quality monitoring, which could be street lighting, which could be drinking water supply or wastewater treatment monitoring. So various edge systems are there. These are all integrated to the smart city IoT platform layer. That means the second tier. That means all the information get aggregated at a platform level. But if you look at it, a city runs in a different gamut. It means there are various stakeholders, there are various departments, there are various, you can say, verticals within the city. So all these things are interconnected. So this entire smart city platform will further get integrated with the overall city-wide management scenario. So you have to look in those three types. So that could be locally, for example, in Andhra Pradesh, we have e-Pragati. E-Pragati is more like an enterprise tier. Whereas individual Ongole, Vijayawada, Visakhapatnam will have a platform tier. And within the city, we'll have various sub-location-wise or system-wide edge networks. So this is how you need to look at. So these are three tiers, as we discussed. At a device layer, this is more relevant to us. The real world generate real-time analog signals, right? End of the day, it is all analog. Whether you digitize it and make it convert into digital, physical parameters are analog. Okay. Fundamentally, digital is a function of analog. So at a device level layer, what we see is real world information coming in a real time, which are sampled by the sensors. That means sensors capture that information in a different sample interval, and they are converted into digital information by the devices. Understand? Sensor samples the physical world, and that is converted into digital form by the things and devices by means of analog to digital conversion or whatever it is. These things, it could be a variety of environments. It could be natural working environment or some other man-made environment like a building or a factory. Now, if you look at the components here, as I said, sensors, it is more like a collection of IoT data beginning with the sensors, because sensor is not an independent element. They are part of an embedded real-time system that samples this analog information, whether it could be video, whether it could be temperature, whether it could be water flow. And the sensor sends the information to the analog to digital. Sometimes, majority of times, sensors also gives the output in the form of digital through some kind of protocol. Fine. But here A to D or something will happen. And finally, the information is sent through some sort of communication interface like I2C, SPI, UART, 4 to 20 milliamp, 4 to 20 milliamp will be converted again to the UART communication like that. So finally, you get some sort of serial bus. And this is then integrated with a microcontroller. So what essentially we are talking is sensors will be connected to the devices, and sensor sampling would be somewhere around 1 millisecond sampling rate for achieving a higher accuracy, and they will be averaged over time depending upon the parameter it is we are sampling, measuring. The things are essentially the embedded systems, which could be a device or an appliance. It may or may not include embedded operating system. It could also be a proprietary kind of embedded software. So it will perform some basic analytics because the sensors will generate high volume of data, right? We are talking about 1 millisecond sampling rate. So you cannot send entire this data, huge data to the platform and cloud, right? You have to perform certain basic analysis and processing at the source of or origin of data itself. So these things and devices essentially act as a basic elementary analysis system. So the next destination would be aggregators or the gateways. Aggregators essentially in industry, we call them data concentrators or the IoT gateways. So what does it do? Processed information comes here. So gateways will talk to various things through various protocols, various interfaces, various request and response modes, or in terms of data streams, and aggregate this entire data and translate into a protocol understandable by the platform. Like it could be simple JSON or REST API or MQTT or COAP like that. So it does all that, and certain control actions also will be taken. Like for example, if temperature is beyond certain limit, locally some buzzer has to be activated. You cannot send the temperature to the central platform layer cloud and take a decision and the command comes from the cloud to the local. It is not possible because communication may break or it may be available or not available. So Murphy's law says if eventually the failure has to happen, it will happen. So there should be some local analytics and also some local decision making and actuation to the physical world. So gateway provides that as well. And other thing you see is an interesting thing. The digital twin will be there. This is a whole new concept, but digital twin you consider it as a replica of a physical system. So now it became more and more natural to run digital twins at the edge. Earlier, digital twins used to be at a central place. Now we are able to deploy digital twins locally. For the time being, forget about what this twin and all. So another thing what we spoke about is the interfaces. Interfaces means how the device layer interacts with the physical world. It could be because here various things are involved. One, what is the parameter being measured? What is the measurement frequency? What is the precision of measurement? What is the physical environment to sensor interface? What is the sensor to controller interface? What is the physical connection, whether it is I2C, SPI? What is the message structure? So these all things are involved here. So these are very much specifications for the physical system. And security, today IoT, if you look at the entire reference model, security will be there across each layer. So device layer security is more like a identification and authentication of device, creating some sort of contextual logs or diagnostic logs within the device. So what is the behavior of system? What are the failures that are occurring in the system? Everything is logged within the system. And also you need to, because in the IoT scenario, every system is connected, right? Tomorrow, if we have to add more functionality to the system, we will update the firmware and upload into the system and run the new firmware. So the security also involves the patch management. This is the device layer for you. So if you look at sensors, we have various sensors, right from position presence to fluids to machine vision. We have a variety of sensors and types. So essentially, we should focus on the working principle. And also placement of sensors and things are very much important. The placement itself decides the accuracy of the measurement and life of the sensor as well. So you need to understand that whether sensors sometimes give direct value or sometimes we have to derive value from the measured parameter. We put it into some equation and we get some other value. So these kinds of things are there. And most importantly, characteristics of sensors is a very critical. What is the accuracy and error? What is the repeatability, reproducibility? What is the tolerance? What is the range? What is the drift or time? What is the resolution of measurement? What is the hysteresis? What is the sensitivity? So when you are working with IoT, particularly deploying sensors, you have to be very careful in these characteristics because the measurement value is entirely dependent on the characteristics. So the calibration and all need to involve these static characteristics. It should factor in these characteristics. So the next layer, if we see the communication, this is interesting because we have in the communication layer, we are talking about stream and the event, right? Event-driven architectures are much more modern, and nowadays everything is event. So even software engineers who are working on IoT and particularly ML and all, they all should be understanding digital logic. Without understanding combinational and sequential logic functions, how they work and how you apply those things, you cannot build event-driven architectures. Event-driven architectures is a more like a, you can say function truth table kind of a scenario. I later, if time permit, I'll explain that. The other thing is the network technology. Then we have communication service providers, and layer interfaces and security are common. So if you see here, we have two types of communication. One is local communication within the edge network, and long range communication, which is across tiers. So local communication connect all IoT devices and endpoints with one or more gateway. Okay. Long range communication is from edge tier to platform tier or to the business tier. So if you see here, physical environment will capture that means there is sense, and IoT endpoint will sense that and also will control the physical environment. Similarly, these all IoT endpoints will get integrated with the edge gateway, which is necessarily not always mandatory, but majority of cases now we are putting edge gateway because we don't want everything to be always connected to cloud. And if you look at long range communication, it is more like a events and data or a data stream coming from the edge gateway. So your central IoT platform gets IoT data and events. So you need to control and manage these edge devices, edge networks. So that one part. What does event-driven architecture mean? Event, generally, change is called an event, right? Many of you are aware of state machines and sequential systems. What is an event? Event is something which is a change, which can be triggered by internal state or could be triggered from external force. Generally, event-driven architectures are like a change is captured and change is communicated. And this is all asynchronous. Information to and fro, everything, processing, triggering, everything is asynchronous. And the system reacts to these events as and when they are received, independent of other things. So event-driven architecture means a generation of events and processing those events and act upon those events. And every IoT platform that is commercially available right now in the market will have the event broker service to talk to these events, capture these events, and support various protocols. And if you look at various protocols, IoT protocols in particular, which more like a event things, advanced message queuing protocol, AMQP, or MQTT, or Kafka, Apache Kafka, or HTTP interfaces, whatever it is. These are all events. And network is more like we build a edge network, right? Whether it is wired or wireless. If it is a wireless, we might have a Bluetooth low energy mesh, or we can have a Wi-Fi, or we can have a low power wide area networks, or low power personal area networks like a Zigbee. So we will have various kinds of networks, and we will manage those network, different kind of topologies. It could be star, it could be mesh. And the third component of communication layer, like I explained, is the communication service providers. Communication service providers are generally people who provide the services. Like if you have to use LoRa, there are various communication service providers. If you are going to use 5G, you will have different SIM card providers and all those things. So these are essentially those communication service providers are part of this layer, because those kind of long-range communication interfaces is what you require. And layer interfaces, like I said, we are talking about communication interfaces. So we have various event-driven architecture protocols, which will dictate client-server kind of scenario. So which will run through Ethernet or IP-based interface. And other thing is some kind of a LoRa. People use for utilities exclusively. They use LoRa communication technology, which is long-range communication. And physical connections through Ethernet is done through Ethernet interface like RJ45 and all. So layer interfaces define all those things. What is the interface? What is the structure? What is the model? Everything. Security is more like authentication, authorization, and encryption. So at a communication layer, there is apart from authentication and authorization, you will have another property, encryption. So we have various encryption techniques. Device level encryption is also now our latest ARM microcontrollers and processors support AES encryption. Zigbee and all by default have those things. So we're talking about various short range to long range communication. And you see here interesting statistics. You could see people are more and more using narrowband IoT and LTE-M. So it is going to increase rapidly. LoRa also, as the utilities are started adopting LoRa for water meters, energy meters, you will see LoRa also gaining some traction. Other providers are there, FlexNet and Sigfox and all, still I doubt, but once 5G is in picture, you will see more and more 5G communication. So in terms of use cases also, for lighting, industrial and consumer electronic related edge networks, people are using Wi-Fi and personal area networks, smartphones and payments and all NFC, whereas controls, building automation and wearables, etc., healthcare, exclusively people are using Bluetooth. So, in a nutshell, we have various communication technologies, interfaces, protocols, and as we are speaking lakhs and lakhs of devices, there is a very complex device management is part of it. We need to monitor the performance of edge networks and edge devices and provide diagnostics things, and various topologies also exist. So you need to understand. So I'm coming into the information layer. Information layer, we looking at data architecture, models, storage, metadata, and interfaces and security. Like I said, they are common. Let us understand what these things are. Data architecture means how your logical data flow will be, how your physical data flow will be. So that data architecture constitutes how you handle the data, how you extract meaningful data without actually structuring the data. So you need to structure the data. You will have a lot of policies, guidelines, and standards you need to comply. And most important thing is your data architecture should be scalable, because things and IoT devices will go on adding in the future. So your data architecture should be scalable. It should not be fixed. And what is data model? Data model describes the way you organize and structure your IoT data for further analytics. How you represent information. So this is very important. Where there are various data models that are available, and for video kind of a use case, there is different data model. For asset data, there is a different data model. For environment related kind of thing, there is a different data model. So data model you should choose and design based on the use case. It cannot be fixed. Then the data storage. Here storage, we already spoke about storage within the device at edge. Here the storage is more like a database. This thing. In IoT, your sequential databases will not work. You require a non-sequential databases or big data. So your data storage is essentially converting data in motion to data in rest, because all your algorithms will reports, dashboards will sit on top of the database, right, in architecture. So you require both maintain historical database as well as the schema, everything. So all the time streaming of real-time streaming processing is not possible. Certain times you need to perform analysis on the data in rest. So your storage is that. There are various storage mechanisms right now. And metadata is very critical for understanding edge behavior and how to use the data. For example, there is a parameter called temperature. If you measure the temperature at edge, that means you measure it in terms of degrees Celsius, then it must be interpreted at the platform tier using the same unit. That means metadata means it provides this information. What is the parameter? What is the way of describing it? If it is a temperature, it is centigrade or Celsius. So same platform also should understand the same thing. So metadata provides that. So as a designer, tomorrow IoT, when you implement, you should have that consistency across the 3 tribes. So standardizing the metadata is a very important activity. And if you don't define properly, consequences would be very different, because maybe your entire automation is based on temperature of 33 degrees centigrade or Celsius, but one at edge it is Fahrenheit, and at IoT platform layer it is Celsius. What will happen? Automation will be in chaos. So you should be very careful. And layer interfaces, we are talking about storage interfaces. Because there are various things, like example, there is a in IoT smart cities environment, people are using PostgreSQL or timescale databases, and certain interfaces they are using big database like Hadoop and all. So interfaces will differ, because sometimes there won't be any platform. Edge device itself has to store data in the database, directly push the data through some sort of API interface. So interfaces is very clear and very important. Security here, since information is already stored, other attributes of security will come, like data theft, data leakage, or attacks from other spurious sources on the data. These all things will come. Now, how you maintain the integrity of data is important here. So this is the information layer. So you will have huge volume of data coming in from variety of forms, and at high speed, and there is uncertainty, which is relevant, which is not. Unless it is analyzed, you are not sure the data is relevant. Next layer is the functional layer. If you see here, as explained, there are two capabilities. Stream processing. The job of stream processing is to ingest the data and make intelligent decisions about what to do next on real time, because there is no time gap available here. On the fly, when the data is getting generated itself, in real time, you need to take decisions and actions. There, stream processing will play a huge role. So in a function layer, in an IoT architecture, IoT platform will have this stream capabilities. It will have stream processing engine, which determines that any incoming data, it will generate a trigger for next action. Like for example, if it found that there is certain pattern, what it should do? It will immediately send a notification to the user, or it will invoke another application, whatever it is. So stream processing engine is a mandatory capability. What is event processing? Events, we talk about change of thing is the event, right? So event processing means some sort of MQTT server or something where there will be there, which will take the events, process those events. Its role is to compare the data with the reference data. That means if you put temperature 33 degrees as a reference or a threshold. So this event processing engine is to check the incoming event data against that policy, like temperature greater than 33 degrees Celsius or not. So it is that capability. So once there is a such kind of a condition fulfilled, then immediately this event processing engine will generate a change event or a trigger event for the application layers. The third component is dispatch and orchestrate. Once after the event processing is done and what should be done is determined, the dispatch and orchestration engine will evoke that particular application, will dispatch the messages in a proper order for resolving that event. Let me take an example to indicate all the three components here. Let us take a building, your own college or university. You are getting temperature data from the monitoring device, some sensor you deployed, and that sensor is continuously capturing temperature within your server room, for example. And this data stream continuously goes into the stream processing engine. It will be processing the data, checks the integrity of data, and further it will go to the event processing engine. Event processing engine, what we have kept, if the temperature is greater than 24 degrees Celsius, switch on particular air conditioning system. So this particular event processing engine will continuously check the incoming data against that particular threshold. Whenever the threshold is fulfilled or that condition is fulfilled, immediately the event processing engine and the policy engine will generate a trigger event for the dispatch and orchestration logic. What it will do, so if temperature is high, this orchestration engine will look into the subscriber's application for that event, like HVAC control application may be there, fire detection application may be there, surveillance application might be there. Immediately it will, whoever subscribes to that particular event, it will dispatch that message in a proper order. So further, that application will take care of whether switch on the system or generate a fire alarm or invoke a video streaming to the security personnel. So this is how it works. So the next other capability of the function layer is the analytics and algorithms. You people are aware of analytics and algorithms. I no longer need to emphasize on it. And advanced analytics is additional capability, machine learning. It may be to identify the pattern or identify the relationship among different parameters or forecast a particular situation. The ML is meant for that. And layer interfaces, as you all know, it is more like APIs, because at a functional layer, various systems talk to each other using APIs. Security, again, it will further includes not only authentication, authorization, and encryption, and also use a identify and protect the system against any abuse of API or denial of services. So this is the finally process layer. We talk about governance, operations, management of systems, business applications, and all. Governance means complete operational management of entire IoT infrastructure, information generated in the IoT infrastructure, services that are being run. Operations is more like a day-to-day standard procedures, how to, what is the automation methodology, what is the business workflows and all. Management deals with device provisioning, like I said, configuration management, change management, version management, password management, system diagnostics, logging, etc. Business application is the end use cases. So layer interfaces, we are looking at a total different. Once, because we are talking about application layer, there will be additional interface, which is called as user interface. Unlike communication and device interfaces, here additionally we will have human machine interface, like a GUI, graphical user interface, or whatever it is. Interaction with the user. Security is a process workflow security and others. You can say application layer security, etc. So these are the IoT, all the layers and the different things. And the interfaces, like I said, across layers within the tier, and cross tier communication will be there. So let us look at in the entire thing. One interesting thing we discussed is you cannot send entire data to the platform. You have to do some sort of data filtering, data cleanup, and finite elementary analysis at the source itself. That means you need to translate the raw information into valuable information. So that is exactly edge computing means. So you will have IoT asset and edge device or edge computer responsibility is to aggregate the data, transform the data, filter the data, and forward the data to the higher layers, which could be platform, which provides analysis and control, or on the cloud, which provides a whole bigger advanced analytics or digital twin kind of capability. So what are the driving factors pushing the designers to implement edge processing? What is the driving factor? I see here 4 driving factors which is pushing the capabilities from cloud to edge. 1, latency. We all learn, right? Speed of light. If I have to achieve the communication speed greater than 1 millisecond, less than 1 millisecond, I need to have a speed of light communication. That means I cannot have more than 100 meters. I cannot have beyond 100 meters. And the cloud cannot go there. Your distance between your IoT device and cloud is in thousands of kilometers or hundreds of kilometers. You don't know. And obviously Ethernet, if you see, the latencies would be in seconds at the end of day, because it has to hop through various nodes. So your latencies are pushing designers to put edge devices. The second is the bandwidth and the data. Imagine 1 millisecond you're sampling every parameter. How many lakhs and lakhs of data bytes you will send every minute? You will be paying huge bandwidth cost. So law of economics, that is also driving to put some sort of intelligence at the edge. The third is the law of regulations. There are security concerns and privacy laws, everything. In fact, in India, even we were asked wherever we are using cloud, government is asking us to ensure that deployment is done in India itself. So nobody wants cloud. You cannot dictate. My cloud should be here only in Andhra Pradesh. You cannot decide that. So law of land, which we call laws and regulations, is also driving the designer to process the data at edge. And other thing is Murphy's law. Interesting. Limited autonomy. Imagine tomorrow there is a communication break. Then the entire functionality of IoT is not available for the user until unless you have some sort of intelligence at edge, which can at least run certain functionality. So these 4 are driving the processing closer to the edge. So I have described here timing here. If it is near edge, it is 1 to 2 milliseconds latency. For edge, platform cloud, you cannot guarantee it will go up to seconds. So look at edge computing. What are the functionality of the edge computing? Here, if you see, interesting aspects is data aggregation 1. That means the aggregating data from the various sources. You can see there is industrial asset, there is a vehicle, there is a camera, there is an embedded device. So you have different interfaces, different communication protocols, different parameters and different sampling rate. So data aggregation is a functionality of edge device which aggregates data from various nodes to minimize the number of connection to the platform. So if you see here cloud platform, it is many to one. In a nutshell, it is reducing the number of direct connection from the device to the cloud. So it acts as a bridge. It could be simple PLC, it could be a vehicle, it could be some kind of a meter or a camera. It doesn't matter. So essentially, if you look into the slide, there are various communication technologies, various protocol structures like a CAN, Modbus, Profibus, OPC, etc., Ethernet, and various kind of data streams, which could be data or it could be a video camera feed. So now data aggregation means it is performing all these things. Then the second functionality of the edge computing is the data normalization. Because raw data cannot be consumed directly by the IoT platform. Because there may be spurious information, there may be some sort of inconsistency. Like for example, your sensor, temperature sensor, at a second zero, it measured as 33 degrees Celsius. Second one, it measured as 71. Second 3, it is measured as 33. This 71 degrees Celsius is a wrong or some mistake, some kind of a spurious measurement. Now, if you don't normalize this information, your platform application will run into problem. So you need to perform normalization. So data normalization is something like a cleaning or correcting the data. There are various protocols we need to support after normalization, like MQTT, COAP, AMQP, XMPP, like that. So machine data is converted using some sort of protocol conversion inside the gateway or the edge device from one form to another. So this is data normalization for you. Data processing, that is 3. Now normalization is cleaning and correcting the measured value. But whether it is possible to send every millisecond data? No, you need to process the data and only send what is relevant. So data processing is that capability of the edge device, which will minimize the traffic sent to the higher order application and reduce the bandwidth cost. So essentially what it is equipped with is data processing capabilities like filtering the outliers, filtering the anomalies, only identify the change rather than sending the same value repeatedly. When there is a change, then only it will send that particular message beyond certain tolerance. So this kind of capabilities is called data processing capabilities. Also, sometimes you need to see cloud and data center or a platform. Sometimes we need to see what is happening inside the edge device. That case, gateways should provide that access, right, to that critical information, which is stored locally. So data processing also involves that capability. The fourth one is the forwarding, is nothing but a routing of data to the different IoT platforms. So processed data is sent further via forwarding through various networks. It could be cellular network or a Ethernet network. Long range communication it uses. So these are the capabilities of the edge. So if you want to implement tomorrow any edge device, you need to understand these IoT layers and the relevant activities performed, and what are the these edge capturing normalization, processing, and forwarding capabilities also you need to implement. Apart from it, there will be some local controls as well, like switching on a relay or something. Some control actions will be there. So this is in a nutshell IoT computation for you. And I introduced the reference architecture and also what exactly happens at edge. So I'll have a hard stop here. We can interact now with the question and answers session. I am ready to answer your queries.
Yes. Thank you, sir. Now I request the participants, any clarifications or doubts. So you can either put it in the chat box or you can raise your hand and you will be unmuted. Sir, please.
Yeah. Do we have any questions?
Participants, you can raise your hand or put your query in the chat box. Sir, there is one question, sir. Will you please brief about COAP protocol purpose?
Okay, COAP actually it is called as constrained application protocol. Generally, there are certain scenarios where we need to use you need to communicate with the constrained devices, and it is very lightweight. Lightweight in the sense, unlike your bulky HTTP protocol, COAP is a very small overhead and all. Generally, it is constraints means there is a power constraint, there is a bandwidth constraint, right? So those kind of scenarios, COAP is used. Whereas MQTT is used where your server is always live and your node is also always live. And the communication is through internet.
So there is one more question, sir. Difference between edge computing and cloud computing.
Okay. See, edge, that is only we discussed. Na? Edge means near to the data source. Cloud means which is far away. So edge computing means performing elementary processing at the source itself. That means, for example, you consider thousands of sensors. Each sensor we are sampling at 1 millisecond rate. We are looking at lakhs of data records per second. You cannot send every second these many lakhs of records to the cloud. So you need to do certain processing. You need to do some basic analysis locally, and then only send the refined data to the cloud. So edge processing, that is what we discussed. Whereas cloud computing is more like you have a processing, everything happens in cloud. Generally, if it is a small, you can say small application, you can perform entire processing in cloud itself. And in cloud, you get compute as a service. That means you'll get infrastructure as a service, all the server, RAM, everything capacity. And you will get platforms as a service. So when you apply those things and implement, your data is processed in a remote cloud server. And the data is sent through internet to the cloud. So that is the difference. Edge means near to the source. Cloud means at the far away, maybe at a centralized location, aggregating everything. Yeah.
Sir, what is a fog computation?
Okay. Let me simplify. Edge means distributed computing. That means at every edge we will have a computation done. That means processing is distributed. Fog means it is more like a aggregating and centrally processing. You can say in tier 2 we use fog computing. Tier 1 near the edge, it is edge computing. It is distributed.
Sir, one more question, sir. Kindly explain how we can do decision making in IoT.
Decision making means what kind of decisions you want. 1 second, let me pull one slide for you. Please be on hold. Can you see my screen?
Yes, sir.
1 second, let me pick the relevant slide for you. Yeah. If you see here, with IoT sensing and all those devices, they generate data. Data has to be translated into action. That's when you get value. So this entire analytics journey, if you see, data, someone, human or machine has to take a decision. Your first step would be understanding what happened. So this we call it as descriptive analytics. So descriptive analytics, first stage you implement that, then you have a big picture of what is happening and what happened. That means you have all the information available in front of you. And then subject matter expert or that particular user will look at the data and decide based on the context and his past experience and initiate action. This is the first step. Once various such kind of decision-making process is documented, or you can say those are made as rules, that means initially first step, the human has performed all the root cause analysis and taken a decision. And second step, going forward, analytics will improve continuously and it will be giving information, that means relationship. This happened because this happened. That means there is a why it happened kind of a post-mortem information available for you. So based on that information, human no longer need to apply brain for root cause analysis. That is there in front. So what decision he or she has to take, that will be taken and action is taken. Now, as and when these various scenarios start occurring, and if you are able to train the machine through machine learning, these kind of scenarios, and machine will forecast, that means it will predict based on the historical data and the present occurring pattern. So this is going to happen. So it will predict and tell the user this is going to happen. And user need to apply that small amount of intelligence. If this is going to happen, what I should do? That decision he or she will take and action will be implemented. Whereas prescriptive analytics, it is a full-scale artificial intelligence where system will tell what user should do. That means system is already decided what to be done and it will inform user to take action. Or if it is an autonomous system like a driverless car, action also it will take. So this is how the decision-making process is done in IoT. You have to start with descriptive analytics, slowly move towards the AI. You cannot straight away jump into the fourth step. Your Google map is a great example. Initially, it initially started telling distance is this much between place A to place B. Later, it started telling uh, uh, this road is like this. These are the possible paths and all. And earlier, this happened that way. It used to take this much time. Later, as the machine learning and artificial intelligence came into picture, it started telling how much time it will take now to go from A to B. Now it has improved further, artificial intelligence. Now it is telling which route you should take, right? It is already reached a stage of decision support. Tomorrow you give that input to the autonomous car, the car will take you. That is the logical path. IoT network and wireless sensor networks. Okay, sorry, I missed a certain thing.
Yes, sir. Actually, the continuation of that is, for examples, if in healthcare, all things are controlled by IoT and certain decisions has to be taken, then how we can do?
Healthcare, if you take, interesting, wearables are mostly going to be your sensors, biomedical sensors are wearables, in particularly the things you wear on your body. It could be a heart rate monitoring, or it could be a simple smartwatch. It doesn't matter. So all the things are essentially capturing the information to the IoT network. But here, decision-making process involves complex diagnosis. So initially, the doctors or the healthcare professionals will be part of it, and only they will use the diagnostic analytics. They won't straight away apply artificial intelligence. It will take certain time and a certain maturity level for the system to automate the decision. Until then, all the diagnostic information will be present to the healthcare expert, and healthcare expert has to take a decision and apply his medical expertise. So that will be there. Whereas for buildings, factories, cars, or up to automations, IoT has moved. Yeah.
Sir, one more question is IoT network and WSN. How are they different? Yes, sir. Okay. Wireless sensor network.
Wireless sensor network, it used to be there. IoT, I said, not just sensing and communication. There is another two elements: analysis and act. Sense, communicate, analyze, act. Other two are not there in WSN. Only sense and communication is there. You bring it to central place, you don't know what next. But here in IoT, we are talking about devices spread across the world, not just a simple localized some part of the facility or a building. Look at a smart city. Everything, entire city, they are spread. You look at pan-India meteorology department's network. They're spread across entire India. And so WSN, you can say a small miniature version, but it doesn't have intelligence, analytical capabilities, and decision-making and acting capabilities, whereas IoT will have. Yeah.
Sir, one more question.
I hope I answered, Pratap. Yeah, go ahead.
Sir, what does IoT device contain?
IoT device essentially is an embedded system having interfaces and connectivity with various sensors. That embedded device essentially is a microcontroller. It can have embedded operating system or RTOS, or may not have. It is not mandatory. And it will have various kinds of services, like it will capture all this information, process the data, store internally, and convert into certain protocol and send through some common cellular or either network to the center place. So IoT
Sir, same madam, they are asking that explain with an example scenario all the layers you explained.
You want that?
Explain with an example scenario all the layers you explained about the IoT device contains, sir. It's a continuation, sir. What does IoT device
Okay.
contain? Explain
Okay.
with an example scenario all the layers you explained.
Can you see the screen?
Yes, sir.
Water distribution monitoring, right?
Yes, sir.
Now, who is that asked the question?
Rajalakshmi. Actually, it was in the private, sir.
Rajalakshmi garu. Okay.
Yes, sir. Rajalakshmi.
Rajalakshmi garu, if you see, this is the one solution space for smart city. It is a drinking water supply monitoring throughout the entire city. If you look at that, right from the river, wherever the water is, or a lake or pond or a tube well, doesn't matter. From the water source to house, you will have various kinds of sensors and IoT devices put across various things, right? If we look at here, interesting concept, in the pump house, there is some kind of a device which is called as energy logging device. That means it is capturing the energy consumption of each pump. And at a treatment plant, there are various sensors like raw water flow sensor, quality sensors like turbidity, pH, conductivity, and chlorine, and what is the level and other etc. And what is the boosting time? That means again energy consumption. That means they are sending the water with certain pressure. So all these are sensors and devices connected to a common RTU, which is called as edge device. It is edge computer. What we used is, it is an embedded system with various sensor interfaces. It has all the data sensing, data normalizing, data processing, data forwarding capabilities. And it will send the data in real time to the platform tier. Here, it could be treatment plant, it could be pump house, it could be your locality, this kind of overhead tank or underground tank. So various data captured, and through various these IoT edge devices, they're sending to the platform through a gateway, right? They're aggregated at a platform layer. And here at a platform, various analytics is done. What is the total localities? How much is the capacity of water that is generated? That means treated. How much is supplied? How many areas got excess supply? How many areas got deficient supply? What are those areas? What are those areas? Morning and evening, how is the schedule run? What is the timeliness? What is the capacity utilization of the treatment plant? And what is the unaccounted for water? That is how much water is wasted from day 1 to day 10. So at a business layer, at an enterprise layer, assuring the water quality at a 90% of time, adhering to the schedule, morning and evening dispatch. And per person, whatever 135 liters described by UN, WHO, whether that is being dispatched or transmitted or not. So all these things are there, starting from sensor layer, IoT devices, edge computing gateway, to the platform, and to the business enterprise applications like these kind of various other applications, right? So this is in a nutshell an example for you to look at all the layers. Yeah. Inke question on that?
Sir, that's all, sir.
Okay. I hope I was able to communicate my knowledge to all of you on the layers, and also what is edge computing and what are the capabilities of edge computing. And if in future, if you have any kind of queries or you want to discuss anything related to IoT, my contact details are available with the organizers. They will share that with you. You can contact me. I'll reply in my convenient time. Yeah. Thank you, Kamaraj Garu. Thanks for the opportunity. I hope you all people gain certain knowledge.
Thank you, Bhavani Shankar Garu. You spent a very good time with us, and uh, our participants are got energized with your lecture on Internet of Things edge processing. Thank you, sir.
Yeah.
Rajshekhar garu.
Yes, sir. Sir, Bhavani Shankar sir, thank you so much, sir, for your valuable time sparing with us and sharing these layers of the protocols and all those things.
Yeah.
And all our participants have been benefited because of your knowledge, sir. Thank you so much,
Yeah.
sir.
Yeah. Thank you. Pleasure is mine.
Thank you.
Thank you, sir. సార్ శ్రీహరి గారు వచ్చారా సార్?
అదే చూస్తున్నానండి, ఇక్కడ కనిపించట్లేదు.
ఇక్కడైతే అంటే ఏ పేరుతో లాగిన్ అయ్యారో తెలియట్లేదు సార్.
నేను చూస్తున్నాను.